fall or ground ice, and that the liquid water would be stable or really even quasi-stable. So in other words, it doesn't just disappear instantly, it disappears over time, but there's some period at which it's present. So because evaporation rates will be very high on Mars, because the pressure is very low, we're probably always in this quasi-stable condition. So let's talk about the theoretical factors. So again, the issues are temperature and pressure. Well, at the Phoenix landing site, which is in the North Polar region, the elevation is fairly low, and because of that, the pressure is always above 6 millibars, which is the triple point pressure of water. So it is the case that you can always have liquid water occurring, being produced from the standpoint of pressure. That is not true at the South Pole, which is 5 kilometers higher. It's a much, Mars is really asymmetric in that way, and all the low terrain is in the north. So, but in the north, you never actually get below the triple point pressure of water. But temperature is a different issue, and this is the basically a climate model showing the amount of insolation that's experienced in the northern hemisphere of Mars as a function of time going back 10 million years. And what you can see is that the amount of insolation is varying all over the place, and it's going up and down, and here we are right now at the present time at about 250 watts per square meter. Now, you also see this high frequency variation, and this is caused by the fact that at the current time, the summer at the northern hemisphere of Mars occurs during aphelion. So in other words, you're out here during northern summer, whereas you're in here during southern summer. And what that turns out, because the orbit of Mars is sufficiently elongated, that makes a very significant difference in the amount of insolation falling at the northern polar region. However, the longitude of perihelion precesses at a 50,000 year cycle. So this means that 25,000 years ago, perihelion occurred in the north. And when that happened, the summer solar flux is 23% stronger than present, so it means it was up here. And climate modelers have looked at this and shown that the temperature, when that occurs, is high enough to allow liquid water to form, pure liquid water to form 10 days a year. So 10 days a year isn't, a fabulous amount of time, but it is enough for microbial growth. So that's the high frequency story. Then you have this low frequency stuff. And what you see is that as you go back in time, you get to higher and higher total insolation. It's like twice as high as present. And that is due to the obliquity of Mars changing. The current obliquity of Mars is 25 degrees, but it goes as high as 45 degrees. And 4 million years ago, it was 45 degrees. At high obliquity, the polar solar flux is 2.5 times the present value, and the temperature exceeds the melting point of pure liquid water 100 days a year. It's actually warmer on Mars during those conditions than it is in Antarctica today. Antarctica of the Earth. So, for that reason, we think that factor is a high. Okay, next thing is there water present at all, and can it be stable? Phoenix found evidence of snow and frost forming under current conditions. This is actually a picture of a way of illustrating the LiDAR data. So again, this is the upward-looking laser and the scattering off of particles. And what you see is that as a function of local time, and this is early in the morning this occurs, you start seeing evidence that particles are falling out of the sky. They're dropping. And the LiDAR only allows you to see down to a couple of 100 meters above the ground. Closer to the ground than that, the LiDAR cuts off. But this is a phenomenon called virga, and on Earth, this is typically associated with snowfall in very thin cloudy conditions. In fact, Virga is responsible for most of the snow that falls in Antarctica in the dry valleys. Furthermore, early in the morning, if you look at the ground on certain days of the year, as we get more into fall, you start seeing white stuff on the ground. You start seeing frost, which is either the snow falling and landing on the ground, or it may be just frost condensation. But in either case, there's a source of water ice onto the ground. Now that's in current conditions. Furthermore, once we started digging into the ground, we encountered ground ice at depths of 3 to 5 centimeters. So there's definitely sources of water. So that factor is high. Again, as I mentioned, evaporation rates on Mars are high on current Mars. So the factor for water stability would be medium. So again, we're multiplying these 4 factors together to get the total. Okay, so that's the story on liquid water. Moving on now to the presence of a biologically available energy source. 2 factors are considered solar and chemical energy. Solar energy is the flux of sunlight in what's called photosynthetically active wavelengths of light. This is obviously the source of most of the biologically available energy on Earth. However, on Mars, you have to shield from sterilizing ultraviolet right at the surface. And the photosynthetically active wavelengths are really only available right at the surface. So the question is there a transparent rock you can crawl under? And the answer appears to be yes. There are, again, seen in the microscopic images, there are semi-transparent glassy grains. And grains like this are capable of blocking ultraviolet and emitting photosynthetically active wavelengths. And they appear to be silica-like. We don't actually know their composition, but it's known that silica sand grains do, in fact, do this. And there are environments like in Antarctica where organisms live underneath the surface of the rock, shielded from UV by exactly this kind of mechanism. So this factor gets a high in the analysis. But there was a new discovery that Phoenix made, which makes the case even stronger, and that is the wet chemistry laboratory in its analysis. Remember, it was capable of measuring these ions of chlorine, nitrogen, phosphorus, and sulfur. And much to our surprise, we found that almost all the chlorine in the soil was tied up in this very unusual compound called perchlorate. Some of you who are aerospace engineers may have heard of this stuff because it is used for rocket fuel. Why is it used for rocket fuel? Because it's a very strong oxidant. Perchlorate is metabolized on Earth by many chemoautotrophs. In order to do chemoautotrophy, which chemoautotrophy means you use chemical energy to support metabolism. So in order to do that, you need to have basically what chemoautotrophy is about is it's about passing electrons back and forth. So you need to have something that can donate electrons and something that can accept electrons. And that's called a redox couple. When you have the right compounds that complement each other, you have a redox couple, and biology can take advantage of that. And on Earth, biology takes advantage of perchlorate as a donor of electrons and methane, hydrogen sulfide, or reduced iron as an acceptor of electrons. Well, we didn't have any way to learn anything about hydrogen. The TIGA didn't see any evidence of methane, although there has been reports of methane on Mars. Hydrogen sulfide was not measurable, and reduced iron would have been measurable by Wickel had we used the right pH of reagent, but we were expecting something kind of different. So we didn't, in fact, have the right pH. We need to have acidic reagents, and we didn't use acidic reagents. But what we do see, again, in the microscopic imaging, is we see these dark grains, and they're magnetic because they stick to the magnetic targets. And typically that means that they're reduced iron in composition. So we think that there is a redox couple that can support chemoautotrophy, so we assign this a high. Okay, so the next factor was the probability that the chemical building blocks of life are available in a biologically available form. So for each element, if it was measured or known to be present, we gave it a high. If it was thought to be in the global soil, we gave it a medium. Phoenix provides direct information only for these elements. So these are the what are called the biogenic elements, SNOPs, or carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the things that you're made of, and bacteria are made of, and trees are made of. Everything on the earth is made, everything living is made of these elements, plus, I mean, dominantly these elements, plus a few trace amounts of other things. Phosphorus we couldn't measure, or did not measure, but it's abundant in Meridiani and Gusev soils, which did have the right instrumentation to measure it. And the SNC meteorites, which are thought to be from Mars, are also high in phosphorus, so we don't think that that's limiting. The highest uncertainty is nitrogen in the form of nitrate. There is nitrogen in the atmosphere, but the biological process for turning nitrogen into something bacteria can use is a difficult, energy-intensive process, and only a very small number of microbes do it. These are called the nitrogen-fixing bacteria. It is not known whether they can work at the low partial pressures of nitrogen found in the Mars atmosphere. So the question of nitrogen in a fixed form is the one measurement that we weren't able to get. Follow-on missions should pay attention to that. The interesting thing is, why couldn't we measure nitrogen? We actually had the capability in WICL to measure nitrogen, we thought. But the ion-selective electrode that was designed to measure nitrogen was 1,000 times more sensitive to the presence of perchlorate than it was to nitrogen. Now, nobody thought perchlorate would be there because it's a very unusual thing to have in the soil. But it clearly was there, and it blew away the ability to measure nitrogen in the soil. Okay, so getting back to my fourth factor, which is or my fourth probability, the probability of a benign environment. Four relevant factors. There's is water activity that's in a range high enough for growth. Water activity has to do with whether water is available to be used by biology, and it has to do with whether salts are present. If you have enough salt present, the water activity gets low and you can't live in highly saline conditions. Now, it's actually a pretty high amount of salinity that bacteria can survive. The only salt that was actually discovered was perchlorate. It's only at 0.5% concentration, so its effect on water activity would be trivial. It actually doesn't even lower it below 99.99%. So the water is available. The pH is moderate. pH 7.7 is about the pH of seawater. So that factor is assigned a high. Organic preservation in the environment. Is the environment allowing organics to stick around, or is it so oxidizing that the organics are destroyed rapidly? This has been a question for a long time on Mars because the Viking experiments, which were sent to Mars to look for life in the 1970s, also had an instrument like the TIGA instrument, similar in fact to the TIGA instrument, to look for organic compounds. And the big discovery of Viking was that there was no organics seen in the soil. Well, as it turns out, that may have been a misinterpretation because, again, nobody was expecting the presence of perchlorate